The femtosecond X-ray experiments instrument is designed and optimized to study ultrafast processes. We study different systems ranging from molecules in solution to hard condensed matter crystalline systems. We use optical laser pulses to initiate a process, for example, a chemical reaction, and femtosecond X-ray pulses to monitor or probe this reaction, and changing the delay, we create a so-called molecular movie. Currently, our temporal resolution reaches 100 femtosecond and even below. This resolution is needed to intrinsically follow the processes, and to do this, we have two different methods. We have spectroscopy and also structural method to study. So the spectroscopy at FXE instrument is divided in two parts. We can do either absorption spectroscopy in the hard X-ray regime or X-ray emission spectroscopy. For the emission spectroscopy, we use two different spectrometers. One is a scanning type or Johann geometry spectrometer, and the other one is the von Hammer spectrometer. The von Hammer spectrometer is dispersive. There is no need to scan the emission line. One can take the entire spectrum in a single shot. On the other hand, the Johann spectrometer needs to be scanned, but it covers much wider solid angle. So the application of the Johann spectrometer is more demanding of photon-hungry experiments. We also use structural methods by doing X-ray scattering. The elastic X-ray scattering is done using the LPD detector. The LPD detector is unique because it's extremely fast. It has a large area and it can also acquire frames with 4.5 megahertz frame rate. 4.5 megahertz is needed to capture all the pulses delivered by the European XFEL machine. At FXE, we also perform X-ray absorption spectroscopy in hard X-ray domain. We do it using the standard 4-bounce monochromator, or we can also perform spectroscopy in a single shot. We have two identical spectrum analyzers which are based on bent diamond crystals and can allow us to record the spectrum of the incoming SARSA beam in a single shot. Single shot diagnostics and single shot measurements are extremely important at free electron lasers because of the nature of the spontaneous process. Every pulse has unique properties and we need to monitor them from shot to shot. Additionally, at the FXE instrument, we have different excitation sources. So we employ pump probe method. So we induce our processes using optical laser pulses. And these laser pulses can be of a different wavelength. For example, we have a tunable system, and we can reach wavelength starting from 300 nanometers up to the infrared domain. Using spectroscopy and scattering methods with femtosecond temporal resolution at FXE, we can study fundamental processes which are very relevant, for example, for solar energy conversion, information storage, or biological function in our body.